All right, so it's my pleasure to welcome you all to the very first Foundations seminar in person of this term. And it's a real delight to have our very own JordanColter over from the physics department. And he's going to tell us about quantum mechanics of the Hartle-Hawking state. So for those joining us on Zoom, you're, as always, welcome to ask questions. Please just raise your hands and I will communicate your question or allow you to talk. And so, Jordan, please.
Well, thank you so much for giving me the opportunity to speak. So I'm going to tell you about the quantum mechanics of the Hartle-Hawking state. And this is joint work in part with Christian Jensen. We had a paper that came out last year upon which most of this talk is based. But I'll also talk about some recent work that came out in this last month, some follow-up work. Of course, feel free to ask questions throughout. I know the audience has different physics backgrounds, so we can always take some of the conversation to the whiteboard if we like. So let me start with this picture. So in the setting of quantum cosmology, we're very interested in asking what is the initial quantum state of the universe, and which state does the universe begin? And we would like to tie this up with the theory of cosmic inflation. We would like, for example, a theory of the initial state, which is coupled to something like an inflaton, that then would make later predictions about CMB fluctuations and reheating and the like. So the basic proposal that is widely beloved by quantum gravity theorists is the Hartle-Hawking proposal. The Hartle-Hawking proposal is that the universe starts off without a boundary. It has a Euclidean cap in the leading term of the topological expansion. And it expands exponentially in a de Sitter-like region in a Lorentzian throat. If we want to get all technical, there should be a sum over different topologies, although the other topologies in the expansion are subleading. The leading contribution, which is often called the Hartle-Hawking state, is one, again, in which the cross-sections of the universe, if you're in 4 dimensions, are 3 spheres. Again, you start with the Euclidean cap, which prepares the state. And then, again, you have that 3-sphere then grows exponentially towards the future. Now, this would be some subleading contribution, for example, where the spatial slices are not 3 spheres, but maybe 3 tori, or S2 plus S1, or something else. But we're going to be concerned with this leading contribution. And when I say the leading contribution, what I mean, just to forecast, is that when you compute these, the wave function of the path integral, that the different terms in this expansion each come with an action, which is associated with the path integral. And this is the contribution that has the largest action. This is, if you like, the highest, naively the highest probability contribution by a huge amount. So in other words, this, if you imagine this with coefficients in ordinary quantum mechanics, the norm squared of this would seemingly, at the semi-classical level, dwarf all of the subleading contributions. So this is the reason that people commonly study this. At a technical level, here's how you should think about the state. So I'm drawing a picture of a space-time, and you might wonder, what does a space-time have to do with the quantum state? So let's imagine, in the setting of pure Einstein gravity in 3 + 1 dimensions, that we have some metric, gamma, that we put at future asymptotia. This is a metric on the 3-sphere at future asymptotia, at very, very late times. We can parameterize a general asymptotically de Sitter metric at asymptotia in this fashion. This is a Pfefferman-Graham expansion, for those who are familiar. And we see that there's this exponential growth, this e to the 2t at late times, and the leading contribution to the metric, the leading spatial metric at asymptotia is given by this gamma ij. Yeah?
Just to understand, are you talking about summing over different future asymptotia?
Well, let's hold that thought. So the question is, this gamma ij is not fixed in the following sense. If we take the Hartle-Hawking state, we can express it in a basis of these metrics. So the way you should think about this is that you should think about the Hartle-Hawking wave function as a functional of the metric at asymptotia. So in the same way, for example, that in ordinary quantum mechanics, you have a wave function psi, and you expand it in the x basis. You can ask, what is psi of x? Given any x, what is the amplitude of the particular wave function? What is the overlap? Here, the same picture is you're asking, what is the probability amplitude that you go from the no boundary state to a metric at future asymptotia with metric gamma asymptotically? That's how you should interpret this object. So again, this is the probability amplitude of having at late times a metric gamma on the 3-sphere. Now, one of the most basic questions you can ask about this object, if you have a wave function, you can compute its correlation functions. That's the first thing you should do. Or that's the second thing you should do, I should say. But the first thing you should do is you should try to make sure you understand how to compute its norm. You would like to check that the norm of the Hartle-Hawking state is something sensible, and moreover, just even know what it means to compute it. How do we actually compute it? Now, I'll explain this in more detail in a little bit, but this is the formal expression for how you would compute the norm of the Hartle-Hawking state. And let me just briefly explain where this formula is coming from. The metric at asymptodia has some gauge redundancy. Because we're in gravity, there is going to be some gauge redundancy that's going to correspond to diffeomorphisms and possibly other things. So on the one hand, at asymptodia, there are diffeomorphisms that correspond to just changing the metric on the sphere, just doing changes of coordinates, if you like, on the asymptotic sphere. Those are redundancies in the description. They are not physical effects. On the other hand, when you define what you mean by asymptodia, there is a Weyl symmetry, a Weyl rescaling that's a gauge redundancy, which is essentially like your choice of asymptotic slice. It's like a time reparameterization, if you like. So really, this gamma is defined modulo diffeomorphisms on the slice, as well as Weyl transformations. So when we want to compute the inner product, what we need to do is we need to integrate over all gamma modulo diff times Weyl. So similarly, if you like, you should just imagine that this formula is a slightly fancier version of what you would do in quantum mechanics. If you wanted to take the norm of a wave function of an ordinary particle, then if it's a function of x, you would take the norm squared and you would integrate over x. Here we're integrating over gamma, which is the asymptotic metrics. That is inside the Hartle-Hawking state because it depends on gamma. But we need to divide out by the gauge redundancy so that we're not overcounting. Is that at least conceptually clear? Good. Okay. And the question is, what does this equal? And then can we use this as a point of departure to compute correlation functions?
Actually,
Yes.
Yeah. It is very clear what you explained. But I'm now thinking about the next subleading guy.
Yes.
The guy with all the topological differences.
Yes.
Is it straightforward how you weight them? I mean, in terms of what are the redundancies and how do you count?
Yeah. So let me tell you briefly where the weighting comes from.
Yeah.
So at tree level, the way the calculation works is that you should compute the classical action of this space-time.
Yeah.
The classical action has two different contributions. It has a contribution coming from the Euclidean cap. It has another contribution that comes from the Lorentzian throat. So when you compute the norm, essentially the contributions from the Lorentzian, what we're going to do is we're going to glue, I have a picture of this on the next slide. We're going to glue this wave function, which is like the ket, to the bra. And in terms of the classical action of the configurations, the Lorentzian and the anti-Lorentzian parts are going to cancel. So the action that survives when you compute the norm at tree level, just the classical action, is just related to the norm of the Euclidean part. Because essentially you have an I and a minus I, which cancels from the Lorentzian part. So the answer essentially is that these are weighted, roughly speaking, by the classical action corresponding to the Euclidean part of the geometry that prepares the state. So you can compute that for different topologies and you get different answers.
Is that different if the topology changes only later, or is the topology already present?
Yeah, that's the
I see. So this is not well indicated in these, since it's slightly hard to draw the pictures at higher dimensions, but you should imagine that the topology, at least the kinds of contributions that are leading, are already present in the shape of the cap. Yeah, it's just a little hard to draw. You can cap off a torus, but it makes for a slightly more complicated picture. Good question, yes.
Do those different topologies belong to the same wave function?
Well, the usual picture that so one way of thinking about this is as follows. The party line would be that we should sum over all geometries which are asymptotically de Sitter and which cap off smoothly in the bulk. Now, one could argue whether this is the right prescription or not, but this is, this is a choice that seems very reasonable and comports with our intuition about how we sum over geometries in the context of string theory. But if you like, for the purposes of this talk, you could ignore the other contributions for now and just take the leading contribution, which is a sphere cross-section, as our main wave function of interest, and we can ask later about what the other ones mean. And they'll become a little bit important in a bit. Yes?
I asked this question, very worried that I'm going to derail the discussion. So I want to delay this to the end.
Yes.
It's fine. I did want to just signpost this.
Uh-huh.
You've been using words like probability and correlation functions.
Yeah.
Now, in the Dirac-von Neumann axioms, the quantum state of the wave function yields probabilities and correlations, quantum functions, and so forth. But these have a very concrete meaning.
Mm-hmm.
They're the probabilities with which a measurement by a macroscopic external observer will obtain certain results.
Mm-hmm.
And the correlation functions are correlation functions in that sense.
Yes.
I should just say, just to begin, I'm very skeptical of quantum cosmology in general, but I don't know what these are probabilities or correlation functions of. There are no external observers to the universe. So are we working on some, like, what are the, I know how to do quantum mechanics if you give me some axioms to work with, but help me understand, what are these, why should I think these are probabilities of anything? What are they probabilities of?
So there's two answers to the question. So let me give you the more party line answer, and then I will tell you.
I love party line answers.
Great. I'll give you the party line answer, and then I'll give you the interesting wrinkle.
Sure.
The party line answer is going to be contingent on a particular condition which was not previously checked, which we will discuss in this talk. But here's the party line answer. So suppose instead, so here we've just been considering pure gravity. We've only talked about the metric. But suppose I coupled it to something like an inflaton and other matter fields, if you like. So what you could do is that you could compute, we could talk about what they mean. You can compute correlation functions at asymptote. You can stick in operators. You could look at fluctuations of the, the scalar and tensor fluctuations of the metric and of the dilaton. And you could use that, for example, if you process it in a certain way to predict CMB fluctuations. So the way, and in fact, many of those predictions agree beautifully with the experiment, but not all of them, importantly. But that's some other subtlety. And so the way, the party line then is that what you imagine is that there is, so let me say this in two ways. The first way is that you imagine that there are meta observers, if you like. That's what they literally call them. I know you don't like that. You won't like that terminology, but I know you well enough to you won't like that terminology. But where you imagine that there are sort of observers who exist after inflation has ended, who can after reheating and everything, who can make observations, and kind of as that there's some argument that one can make that you can have those correspond to operators that are inserted at the slice where sort of inflation comes to an end, and then you can use that to make CMB, predictions of CMB fluctuations, for example. However, that and just to say, and it does, in terms of the the Gaussian spectral fluctuations, I mean, it agrees very well with the Hartle-Hawking state. I mean, so one thing I should say, I guess we're getting a little bit off subject, but let me make one comment about the Hartle-Hawking state that's not widely appreciated, which is quite interesting. It predicts something very wrong about our universe, which is this: when you couple it to an inflaton, it actually predicts that within the type of framework that I was describing, that it pressures the inflaton to undergo as few e-folds of inflation as possible, meaning that you would expect the universe to actually have very, very high spatial curvature, which it does not. So that is, so what people typically do is they just ignore this issue, and you just pretend that you're in a regime in which the universe is actually very large. You ignore that contribution, then you just compute the Gaussian quadratic spectrum of fluctuations, and that part looks great. So there's a phenomenological issue with the Hartle-Hawking state, but we'll come back to that in a little bit.
So they told me that years ago. Yeah,
that's right. So the one other thing, by the way, is that everything that I'm saying, the probability interpretation is predicated on, we should at least compute the norm and see, we should compute these basic objects just to see even if what I said is cogent and hangs together. It's another question. Yes?
I guess, just leading, I don't think it'll take us too much further astray than we already are.
That's fine.
The foundation seminar.
I was going to say it's the foundation
walking.
seminar. We have to ask about the
That's why
foundation.
I feel emboldened to ask these questions. The probability in the meta-observer picture, the probability of computing, I guess, would be, there's no ensemble of experiments that you could carry out. So I guess it would be in a probability in some Bayesian sense. You'd be calculating priors, maybe, of the observer, or of the meta-observer.
Well, you could ask a question about, if you wanted to go down the many worlds route, there's something you could say about that. I mean, I think this will bring us far afield, but let me just say the following. If I give you a wave function of the universe, you should be able to make predictions about the CMB. This makes some predictions about the CMB, and many of them are very, very right, and some of them are very, very wrong. So we should understand what's going on, and we can ask later about the important question of what is the interpretation. But you'll see that there's a wrinkle in the interpretation for a reason that we haven't discussed yet that will be apparent in about 5 minutes. This is good. Feel free to ask these questions too. I mean, this talk we can. There are parts with technical details, but I'd rather you understand the conceptual details because you'll remember that more. Okay, so this was a proposal due to Hartle and Hawking in '83, and a very basic question is, what is the norm of the Hartle-Hawking state? I mean, you might want to know that before you compute correlation functions, just to know how to do it. Okay, so what you do is that you glue the ket to the bra. This is the kind of picture that I was advocating before. The level of picture analysis, what would you expect the answer to be? Well, the level of looking at the pictures, you might expect that the Lorentzian and the anti-Lorentzian parts are going to cancel, and that maybe the norm would be related to a sphere, because the Euclidean cap and the anti-cap would combine to give you a sphere. This, in fact, was the expectation of what the answer should look like. Well, let me make a comment about this. The equality of these two expressions is true at tree level, but it's not obviously true at loop level when you incorporate fluctuations of the space-time. Let me explain briefly why. There are many, many subtleties, but among them is this. The Hartle-Hawking wave function factorizes at tree level, like when you look at its leading saddle, into a Euclidean piece and a Lorentzian piece. And therefore, you would expect that on the actual tree level saddle, that the classical saddle, that the Lorentzian and the anti-Lorentzian parts would cancel, leaving you with the two Euclidean pieces, which give you the sphere. However, when you look at fluctuations around the space-time, when you look at fluctuations where you integrate over this geometry gamma at infinity, if you try to fill in what the rest of the space-time looks like, it'll be generally a complex, smooth metric that will not have just a Lorentzian piece and a Euclidean piece that cleanly separate. It'll in general have complex fluctuations that will pervade the entire space-time. And therefore, you don't expect that there's necessarily going to be a clean cancellation between the Lorentzian and anti-Lorentzian parts once you take the quantum fluctuations into account. But nonetheless, the hope is that, or something that people thought, I think, for a long time, was that the computation would reorganize into one where you would just compute the sphere partition function, this is Euclidean quantity, at one loop, and that somehow the one loop norm would agree with the one loop partition function. That was the guess. There's an interesting famous fact about this partition function, which is famous for other reasons because it computes the static patch entropy in de Sitter. Polchinski tried to not tried, but successfully computed this to one loop, the sphere partition function. And the sphere partition function, this was a paper in '89, goes like e to the entropy. This is the answer that you would expect, e to the de Sitter entropy, but it has a factor of I to the d plus 2 in it. So if you're working in 4 dimensions, famously, you're going to get I to the 6th power is not positive. So this is a very strange answer if it's related to an entropy counting. It's also a strange answer if you think it should be related to the norm of a state. So already we see that there is some tension between guessing that the norm of the Hartle-Hawking state is going to be related to the sphere, because the sphere is not even in 4 dimensions a positive number. That is not very befitting of a positive definite norm of the state.
Is it possible to give us an idea of what's generating this I?
Yeah, so I have some backup slides about this in detail, but let me tell you in a few sentences. So essentially what happens is that there are, in Euclidean gravity, there's this famous problem with the conformal mode that has the wrong sign. So the usual thing that people do, the prescription is that you can change the contour, you can essentially rotate it so that it becomes positive. But if you look at its spectrum of fluctuations, that even upon rotating it, there is a finite number of wrong sign modes, even after you rotate it. So you have to rotate those finite number of modes back. So then when you handle this in zeta reg, essentially that gives you a finite number of factors of I. So this is actually the answer that we'll find at one loop.
Has anyone computed this in conformal gravity?
I believe so, but I don't know what the answer is. Yeah, good question. So the answer that we're going to find at one loop for the norm of the Hartle-Hawking state is not the sphere, does not agree with the sphere partition function in a crucial way. It has a numerator which looks, in a certain sense, like the absolute value of the sphere partition function. I can describe some subtleties in that. But the important feature is that it has a division by the volume of SOD1. And SOD1, if you're a d-dimensional de Sitter, is the, well, there's two notable things about it. One is that it's the de Sitter isometry group, okay? I should say that in the computation of the sphere partition function, there's also a volume factor, but it's SOD plus 1 instead of SOD1. Anyway. But a notable feature of SOD1 is that it's a non-compact group, and therefore its volume is infinite. Therefore, what this suggests is that the norm of the Hartle-Hawking state to one loop is actually equal to 0, because it's a finite number in zeta reg divided by an infinity. So this would suggest that the leading contribution to the no boundary, so in the sum over topology, is that the contribution corresponding to three-sphere cross-sections actually has 0 amplitude.
Well, it's your paper, Cotler, I just can't see because
Oh yes, this is the Cotler-Jensen paper from this last summer. Yes?
Is this because the gravity no longer fluctuates at an asymptotia? Asymptotia is infinitely far away.
No, we are integrating over. We're integrating over all of these gamma metrics at infinity. I mean, it's not an asymptotically cold spacetime. Maybe that's your in ADS you can have that picture, but not in DS. If you shoot a graviton, for example, at finite time, it is going to be there in the far future.
So this is saying that the tree level is 0.
This is saying that the loop level is 0.
The loop level.
Yeah, the tree level is finite, but the loop level is 0. In fact, something I'll explain later is you can compute this to all loops by a pretty interesting recursion argument, and it's actually 0 to all loops. Yes?
Sir, I missed why to divide by the volume of SOD.
Oh, I haven't explained why yet.
Because we are integrating only over the spatial metrics, right?
Yeah,
the
the rest of the talk will explain where this comes from, but it's not obvious at this point.
Okay, thank you.
Okay, so the Hartle-Hawking contribution then is a null state at one loop, and in fact, hold on one second, to all higher loops. And if you couple it to Bunch-Davies matter, that is to say, you might want to couple it to matter that's also jointly in the no boundary state, that does not affect the argument, and it's still a null state. So it's sort of, so in other words, we've been talking about pure gravity, but if you included matter in the sensible way, it wouldn't affect the conclusion. Dane, yeah?
Is this related at all to the minus sign on the previous slide, or in some non-trivial way?
For an interesting reason we'll see later, there isn't actually a minus sign in this calculation for a physics reason.
Okay.
So you might wonder whether it's a negative number divided by infinity, for example. Well, I put an absolute value here suggestively, but in fact it's not, for an interesting reason. One way of understanding this is that the conformal, in this calculation, there isn't a conformal mode essentially because vial is pure diff. That's one way to think about it. That's a slightly imprecise way to phrase it, but that's the basic intuition. Okay.
I got confused. The calculation on the previous slide was not the one loop one?
So on the previous slide, there's a question mark, which is to say, you might have guessed that these two were equal. But in fact, this is not true. And this is now proportionality. I guess I'm using 2B symbols. Because there's a constant prefactor that's order 1, but the answer is that it's 0. If you're proportional to 0, you also happen to be 0. Okay. So are there any questions maybe before? So the plan of the rest of this talk, and whatever time we have left, is going to be explaining to you where this division by volume of SOD1 comes from. It's a physical effect. It's quite interesting. I'll also say briefly about why it persists to all higher loops. That's both subtle and interesting. But are there any questions about the basic premise of? Now, the question you might have, which we could talk about at the end, is, well, what does this mean? What does it mean that this is a null state? It's a good question. There's a few thoughts on that.
Well, I thought it's not a real state.
At tree level, it's.
Well, the whole thing is not zero.
Sure it is. What do you mean the whole thing? The Hartle-Hawking, I mean, the higher topological
norm.
contributions may not be zero.
But the norm entirely is zero.
The norm entirely of the Hartle-Hawking state?
Oh.
It is. That's what I'm saying.
Okay.
I think Hung just asking, this is at one loop, but the tree level calculation is also zero, not zero.
Well, the tree level is just looking at the classical action, but the one loop effects multiply the class. So it's
Oh, yeah, okay.
okay. So let me say a bit about the inner product on asymptotic states. So we look at the inner product in asymptotic states. So there was a nice discussion of this in this paper from 2023, but then that Christian and I used in our calculation. So as I pointed out, the natural set of fields that you're integrating over are these metrics at asymptotia gamma modulo diff times while, modulo their gauge redundancy. And this, one way of articulating this is that what we're doing is that we're taking the psi of gamma, that's the wave function, we're inserting a resolution of the identity in this gamma basis, where we're putting in these gammas modulo diff times while. Now, for reasons that aren't particularly important, I will sometimes put double brackets on my bras and cats, which distinguish that these are states in gravity as opposed to in quantum mechanics, where we have to be attentive to gauge redundancies. So let's proceed to compute the norm of the Hartle-Hawking contribution to the no boundary state, to one loop, at first in pure gravity. Again, what I mean by this notation is that the no boundary state is viewed as the sum over all topologies, the Hartle-Hawking plus the torus, the S2 cross S, it's the sum over all of these things. But so the Hartle-Hawking state is like the leading contribution of that superposition, if you like. Well, the thing that you would expect to be leading, but apparently it's not leading because it has norm zero. So you might have expected that it would be the most dominant contribution, but at least in pure gravity and gravity coupled to Bunch-Davies matter, it's not. So here's the norm. So let me expand what we mean by the Hartle-Hawking wave function. So the Hartle-Hawking wave function, just to remind you, is that you take the Einstein-Hilbert action in the path integral. So this is now we're integrating over metrics mod bulk diffeomorphisms. You have the no boundary, this is a schematic, you have the no boundary condition in the far past, and you integrate up to geometries at asymptotia that terminate in an asymptotic metric gamma. So this literally is some schematic of the definition of the Hartle-Hawking state itself. One can be more precise about this, but I just want to show you what it means in the ordinary path integral language. If you're computing this integral over gamma, you can ask if there's any saddle point in gamma. So you can ask, what does it mean to do this calculation at one loop? The leading contribution comes from gamma. So again, we're integrating over these metrics. So we're gluing together this bra and the ket where we're integrating over metrics on a three-sphere. And there's a single metric that dominates this, which is the round metric. I'm going to call it gamma naught. It's just the ordinary canonical metric on the three-sphere. You can consider many other metrics on the three-sphere that are not the round metric, but the round metric is the one that dominates in the expansions, the saddle point. Now, if you asked what is the bulk metric, so if you set up the round metric on the asymptotic sphere and then worked backwards and figured out what the bulk geometry looks like, you would get the Hartle-Hawking geometry that I explained to you from before. Let me make a few comments about it. So the bulk metric that corresponds to this saddle is the ordinary de Sitter geometry, where when you go down to t equals 0, you then continue the path, the time contour into the imaginary plane, into the imaginary axis, so that the space pinches off into a Euclidean hemisphere. So this is to say that this geometry here is the one that corresponds to the leading saddle point contribution to the norm. in a way, this is just justifying the pictures that I've already shown you. Yeah.
Does the pinch off create something like a tension term, or it doesn't?
No, it smoothly pinches off. There isn't any tension term for the Hartle-Hawking geometry. I mean, you might be worried about the interface, the curvatures match.
Yeah. The curve.
One way of understanding this is that you can think about it as a, let me not go into it.
Sorry,
Yeah.
one question about this path integral. So this was some UV cutoff. So
We're doing this in EFT.
Right.
So the blue bit is Euclidean and then you're Victorine, is that so?
I would just say that we're defining the Hartle-Hawking geometry along a complex time contour. This is just a rearticulation of the ordinary geometry. So there's one way that you would say this, that you take a Lorentzian part and you take a Euclidean part and you glue them together at the bottleneck in such a way that the induced curvatures align. Right. In other words, that there's not some tension or something like that. I mean, that's the ordinary picture. But a different way you can think about it is just to take the global metric on de Sitter and then consider it along a complex time contour, and it gives you the same geometry. Yeah.
Just so I understand the zero you're getting is coming from dividing by this huge volume of this gauge group.
Yeah, I haven't said where that comes from yet.
Okay. Yeah, maybe you're going to get to it. I was going to kind of ask if the feeling of the cardinality of are we dividing by the naturals or the reals, or, but I'm trying to think if I wanted to cancel this, if I wanted to evade this somehow, how bad of an infinity?
Well, one way to think about it is to think about the Haar integral over SOD1.
Yeah.
You can do a kind of Gauss decomposition of that.
Yeah.
So, I mean, if you like, maybe here's a different picture. If you take SOD1 and you mod it out by rotations, just SOD,
yeah,
and you're going to get basically hyperbolic. The coset is like a hyperbolic space, so it's like the volume of hyperbolic space.
Okay. Yeah.
Okay. So what we're going to do, which is hiding behind my my thing, is that we're going to expand the metric. Don't worry, I have this memorized. In which you take gamma and you expand it around gamma naught, which is the metric on the round sphere, plus root g times h, where h is the fluctuations. This is what you would do when you compute a one-loop computation. You do some expansion. Okay. So let's consider now the Hartle-Hawking state evaluated a little bit away from the metric on the round sphere. So this is the metric on the round sphere plus little tiny fluctuations away from that. I'm going to write this as the Hartle-Hawking state where we smash it against a bra, which is gamma naught plus root gh. We can compute what this wave function is at one loop. It has a tree level piece, so e to the s naught over 2. It has a one loop prefactor. And then it has some dependence, some Gaussian dependence on the fluctuations away from the round metric on the sphere. This is exactly what you would expect from a one-loop calculation. This is a bit schematic, so let me tell you what the actual form of the answer is. So let's look at this exponential piece, namely what the dependence is on the fluctuations away from the metric on the round sphere. So it's a Gaussian, and what is the form of the Gaussian? So the form of the Gaussian, which you can deduce basically by word identities, is that, so there's an Hij and HKL, which are contracted against some kernel. And I've written the kernel suggestively as the stress tensor two-point function on the 3 sphere. I've written this in general dimension because the argument doesn't really depend on 3 dimensions. So it's actually the stress tensor correlation function on the d-1 sphere. So you shouldn't, I'm not saying that there is something like a holographic dual or something. This is just to organize what the kernel looks like. It's that if you have a CFT stress tensor on the d-1 sphere, there's a universal form for its two-point function. That is the form of the quadratic kernel. Yes?
So is it a Euclidean path integral? I don't see eyes floating around.
Well, this is a wave function. There is a Euclidean Lorentzian path integral, this complex geometry that is preparing the wave function of asymptotia. And this is describing a metric which is on a spatial slice.
Oh, spatial slice.
So that's why we're looking at fluctuations of the metric on this d-1 sphere. So there's no i's anymore. So this, anyway, is the form of the quadratic kernel. And I want to make a few comments about it. Let's focus on d even for now. So 4 dimensions is a good even number to avoid the complications of anomalies. So the simplest way to understand the result is that the late time de Sitter wave functions behave like CFT partition functions in d-1 dimensions coupled to sources, including a metric gamma. This is all to say, you don't need to parse that sentence if you want. It just means that this is the form of the quadratic fluctuations. But the kernel, again, looks like a stress tensor 2-point function. Now, the key feature of this is the following. This kernel does not have any bosonic zero modes. In other words, there's no zero directions. So you can do this Gaussian integral without running into infinities. And it has no wrong sign modes. Dane, this is related to your question from before. There are no wrong sign modes. So that's a difference from this separate calculation on the Euclidean sphere of just gravity on the sphere. This is a different calculation. This is not Euclidean gravity on the sphere, but this amplitude produced by the Hartle-Hawking state, computing that norm, which is related to a different integral of different degrees of freedom on the d-1 sphere. Moreover, the wave function is SOD1 invariant, as befitting of, essentially because the background geometry is SOD1 invariant, the one-loop fluctuations around it looks like putting spin-2 fields on a background, and they inherit the SOD1 invariance, if you like. Okay, so where does this SOD1 volume factor come from? What's going on? Well, let me give you a sketch of the computation. The sketch of the computation is that the Hartle-Hawking state at one loop is a Gaussian over fluctuations of the metric at future infinity around the round sphere. This is to say that I showed you that the wave function itself is a Gaussian at one loop, and you know how to do Gaussian integrals, and that's all fine. That part is no problem. Moreover, the round sphere, gamma equals gamma naught, is a stable saddle point of the one-loop norm. This is to say that there's justification for doing this expansion around the round metric. But here's the key point. To integrate over fluctuations, to integrate over these gammas, we must gauge fix the diff times Weyl symmetry via the Fedotov-Popov procedure. In other words, we don't want to overcount the gammas. So for example, you could fix the non-transverse traceless fluctuations of gamma to vanish. This is, it's a particular gauge fixing that would fix the diff and Weyl. Now, here's the key point. Because of the fact that the wave function has no bosonic zero modes, when we do that Gaussian integral, we're not going to get zeros. We're not going to get volume factors from that. However, when you fix the diff times Weyl transformations, there are ghost zero modes, which correspond to residual diff times Weyl transformations that have not been fixed. And in fact, you get an SOD1's worth of those fermionic zero modes corresponding to conformal isometries. But these are symmetries of the wave function. I'll say this in a few different ways so that it parses, because this is not a totally obvious fact. So therefore, if we integrate over bosonic zero modes, non-zero ghost modes, and divide by the volume of the residual SOD1 symmetry, this produces this 1 over volume of SOD1, which I described. So let me say this in a few different ways, because this is sort of the central point. So when you do the gauge fixing of the diff times Weyl, we gauge fix gamma under diff times Weyl. It turns out that the natural gauge fixing that you would do at one loop has some unfixed gauge transformations, which correspond to these SOD1 transformations. So we separately have to divide out by them. We have to additionally fix them. However, we do not have any corresponding bosonic zero modes to cancel them. So what's strange is that the wave function is SOD1 invariant, but it has no bosonic zero modes. So therefore, there are no bosonic zero modes in the wave function that can cancel out the fermionic zero modes coming from the ghost sector. And that's why you get a 1 over volume of SOD1, SOD comma 1. Now a comment. The same thing happens in the computation of the sphere partition function. It's just that you get a volume of SOD plus 1. And that's a finite number. Let me maybe make a comment over on the board just so that to orient us. This fact that might be confusing of why you can have a wave function that has some symmetry but no zero modes is actually a very familiar fact that I want to remind you of. If you just have a, whoops, let's do this one. The nice thing about chalk is that you know when it's used up.
You can tap that down and put it right back on the tray.
Well, that's the whole cultural. That's the joy of using that. Okay, so if we had, for example, a Gaussian integral, let's say e to the minus, 1 over norm of x squared. Or sorry, this is just 1/2 times norm of x squared. This is a Gaussian integral. This Gaussian integral, this x, is invariant under SON transformations. But this Gaussian has no zero modes. It's perfectly non-degenerate. So what we're seeing is an infinite dimensional avatar of this fact, but now in terms of these more complicated SOD1 transformations, in which we have a wave function which is invariant under a symmetry, but has a perfectly non-degenerate kernel. So the integration over the matter fields themselves, sorry, thanks for the camera work.
That's totally fine.
The integration over the fields themselves is not going to give us, volume factors. But the gauge fixing redundancy is going to give us volume factors. So a comment in this case, you don't have to turn back to it, but the Gaussian case that the people joining online will remember, if you wanted to gauge this by SON transformations, the answer would be proportional to 1 over the volume of SON. So you could do a finite dimensional version of this to convince yourself, if you like, that the phenomena is somewhat mundane once you put all the facts together. Yes?
Oh, sorry, you can go for it. Oh, right, sorry, yeah. Sorry, I just wanted to check. So, the difficult vial for the little gammas, these are large gauge transformations from the point of view of the bulk theory. Is it correct to gauge these out?
Well,
because this is the source of your.
Well, the point is that gamma itself the point is that gamma itself is only defined modulo diff times Weyl transformations. It's the same. It corresponds to the same physical wave function.
Well, I agree. When it's not asymptotic boundary, but when it's an asymptotic boundary, then these are large gauge transformations from the point of view of the bulk theory, which are.
He's going to take a norm, so it's no longer an asymptotic. Yeah.
Yeah, but where this volume factor comes from, the kills all the things, comes from those large gauge transformations.
Well,
so it's the difficult vial.
Only the norm.
Yeah. Sorry.
Yeah, I'm in the norm.
Yeah, I'm questioning the prescription. Why the integral when gamma has the difficult vial?
This is a redundancy of what you even mean by the asymptotic metric. So let me say it a different way, if you like. There's a way of doing this is work in progress. There's a way of doing this calculation at finite time. It also works at finite time.
Oh. But that's I'm happy with that, right? I'm happy with that bit. Yeah. I'm talking about this part where it's asymptotic symmetry, because you expect your Weber fields to transform in representations of your large gauge transformations, right? This is something we are familiar with in the celestial community, right? We want.
Well, let me make a comment. So one comment is that let me make there's a few ways of articulating this. Suppose instead of working in the global slicing where the cross sections were spheres, that we worked in flat slicing where asymptotia becomes r to the d minus 1. Now, as a comment, this is not. Flat slicing is not geodesically complete, so it has some other issues, but anyway. So in that case, I would not gauge by SOD1, in the same reason that in flat space you wouldn't gauge by the Poincare group. I think that's the analogy that you're imagining. If the point is that the slice in which we're working is compact. I think the thing that you're imagining, which is true, is that if you worked in a space where you had a slice that was non-compact, then you would want to only divide by gauge transformations which don't run off to infinity.
I'm not worried about large on this slice. I'm worried about large time, right? It's a infinity in time. But okay, but I mean, if this is the prescription, then I need to,
Yeah, I mean, I would say that this is just, I mean, you how do I put this? This is like time reparameterizations, if you like. This is just about the definition of sort of where your cutoff slice is.
I mean, the fact that we're using gamma, the leading term in the grammar expression means that we're taking time to infinite.
In a holographically renormalized sense, yes, if you like, but that's just about the addition of counter terms.
And sorry, sorry to keep delaying your question, but another question is that maybe I'm about to come to this, but the different topologies, you have less and less killing vectors.
Yes.
Oh, you're about to go there.
Oh, well, I'll mention it, but in short, for the other subleading topologies, they're going to break the SOD1 down to a compact subgroup, so they won't have this problem.
Yeah. So I was going to ask, so now these are your things that we call subleading. I guess they are the only things that.
In pure gravity coupled to bunch dB symmetrics, right?
Thank you. Sorry.
Yeah, good question.
We can chat afterwards.
Quick question.
Yes.
The bosonic zero modes would have been spin 2 zero modes, so you're saying there are vectorial zero modes, but no spin 2 zero modes here.
Well, they come from the ghost sector,
Yeah. So
not from the wave function.
Right.
Yeah, that's right. Anyway, so the answer that we find, you can be a bit more careful about the dependence on S naught, which is the entropy. These are like factors of M plot and things like that. But the basic answer is that you find this division by the volume of SOD1 in one loop. And what we find is that the norm of the Hartle-Hawking state in pure gravity is 0 to 1 loop. Now we can compare this, by the way, with the ordinary sphere partition function, which has this factor of I to the d plus 2. It also has this division by volume of SOD plus 1. So it has some superficial similarities, but it's not 0. Rather, the sphere partition function is not 0, because it has a different gauge group, or a different symmetric group. Now, one comment is that in 3D gravity, one can show that the calculation is one loop exact, and in particular that the norm is 0 to all loops. One way of understanding this, so in other words, it's easy to show that the norm is 0 to all loops in the 3D case because it's one loop exact. The reason it's one loop exact is in 3D, the only metric on the two-sphere mod diff times vial is gauge equivalent to the round metric. So you don't really even have to integrate over fluctuations. This is related to the familiar fact that the bosonic string partition function is proportional to 1 over the volume of PSL2C, which is famously, this is equal to 0. For the same reason as division by this infinite volume.
That was my question.
Yeah. So there is a precise sense in which in 3D gravity there is a kind of connection, there's a kind of stringy description, if you like, of sort of 3D, of the wave function asymptotia. So this fact is not a coincidental connection.
But people don't think it's an issue, right?
It's not an issue because it has a different interpretation.
Well, but the interpretation of that is that it computes after appropriate integration over the moduli space as S matrix. Where for Hartle-Hawking state, you can say that its interpretation of that is that it only computes the correlation.
Well, hold that thought.
Oh, okay.
The norm of the conformal invariant factor is 0 and string theory, right? Unless you have 3 zero modes.
Yeah, that's true.
Yeah. Well, the problem is that, well, let me just make a comment. The problem, at least in this context, what happens in the stringy case, let me not comment on that for a moment, is that when you compute correlation functions, you're supposed to divide by the norm. I mean, if you have an unnormalized state, compute the correlate, compute psi, operator, psi, and then you divide by the norm. If you didn't do that, then in this case, at the very least, so then you would get the correlation functions would be proportional to e to the s naught. I mean, it would be as large as the exponential of the entropy. I mean, a different way of saying this is that there's this funny fact that there's something wrong with a probabilistic interpretation because, as you say, if you insert operators, you will break the SOD1 symmetry if you put enough operators. So that will render correlation functions of the state as being finite. However, you can't compute normalized correlation functions because the norm is 0. So that's very strange indeed.
You remove the null state from your Hilbert space, choose a better vacuum.
Well, the answer is that you can. There's subleading contributions, and those are fine that correspond to the higher topologies or other things. Yes.
So in for example, in asymptotically flat spacetimes, we as was discussed not long ago, you shouldn't consider the asymptotic symmetry group as being part of your gauge group.
Right.
But in the origins of that statement are that or at least, well, if you want a quantum theory that respects the structure of the classical theory, then in the classical theory, the symplectic form is non-degenerate on those large gauge transformations, so they are really physical, they're different physical points in phase space, even though they're symmetric.
Yeah.
Okay. So then, if I want to run a similar argument here, right? Are all of the let's say symmetries whose volume you're dividing by degeneracies of the symplectic form, or is that clear?
I haven't thought about it in that language, so let me not say the wrong thing. But I get well. Yeah, let me not try to say it in real time, but rather in imaginary time. Okay. So in the interest of time, let me just make some comments. So there's this subtlety about, this is hiding. I'll just get to the punchline here. So what we found, a key feature in the argument is that there are these fermion zero modes of the ghost sector, which become deformed if you look at higher loop corrections. You no longer get the ordinary conformal killing vectors. But an interesting argument which appeared in a paper in the last week, in which you can show that there's some deformation of the conformal killing vectors, roughly speaking, which still satisfy the SOD1 algebra, which end up furnishing a representation of SOD1 to all loops in perturbation theory, and end up, in short, being able to allow you to generalize this argument to all loops. I don't have time to go into it. It's not explained here, but you can take a look at the paper if you're interested. If we add Bunch-Davies matter, this doesn't change the form of the result, at least at one loop, and in fact, at higher loops, it likewise doesn't change it for a slightly trickier reason. But at least at one loop, the answer is simple. It's that if you include Bunch-Davies matter, the wave function factorizes at one loop. And the product of these things is still SOD1 invariant. So roughly speaking, the norm factorizes into these two pieces. And if this term is 0, then the product of both of them is likewise 0. Now for the slow roll inflaton, well, the one loop inflaton wave function is SOD1 invariant, but it also has this linear term. This is related to this fact that I was saying that the Hartle-Hawking version of the Hartle-Hawking state with the inflaton coupled to gravity has this pressure for as little inflation to happen as possible. So we're in this weird situation in inflation where we still have these SOD1 factors, but this one loop inflaton state is not itself normalizable because of this linear term. So you have in that sense a kind of infinity upstairs, and an infinity that's coming from the fact that you can't really do the integral over the inflaton field. So that's a slightly confusing state of affairs that I'm trying to sort out what's going on. Well, this is wishful thinking. The problem does not go away. That's an earlier version of it. Okay. one other thing to say is that we can also couple to a world line. So in the interest of time, I won't explain the details, but here's the picture you should have in your head. You can imagine that there is a world line. So a world line in the context of the Hartle-Hawking state is one where you have a creation of two different parts of the world line from the Euclidean cap, one that goes off to infinity, another that goes off to infinity at the antipodal point. This is the saddle approximation. And then you can glue the cap to the bra in the ordinary way. And what you find is that so the world line actually breaks most of the boost, except for an SO11 of your spacetime. But it turns out that there is a bosonic zero mode coming from global time shifts along the world line that ends up canceling out the volume of SO11 downstairs. So you end up getting a finite answer. The words that you would associate to this is an observer, a world line with some degrees of freedom attached to it, that have a lot of entropy, gives a finite inner product. This suggests a connection to some recent work by Chandrasekhar Longo, Pennington, and Whitten. But to my own intuition, the fact that putting in a world line renders the answer finite, I think, is a red herring. To me, it seems. I don't think. When you do CMB fluctuations, you don't usually put in a world line to get finite answers. That seems kind of like a hack.
You have matter.
But the matter in the Bunch-Davies vacuum is not going to help us.
Couldn't use bosonic zero modes?
The ordinary matter that we consider doesn't have the kinds of bosonic zero, doesn't really have the bosonic zero modes that would cancel this. I mean, you could consider the natural matter that you would put in that you have in mind is not going to help, unfortunately. The inflaton, again, is this other weird situation because it has this non-normalizable part of the wave function, but that's a separate issue.
So is that thing in the blue, is that supposed to rescue sort of the physicality?
Let me just say that this is an observation without a good interpretation.
Okay.
This is something that you might want to try because people are really interested in world lines in the context of de Sitter. And to say it in the most dispassionate way, I'm reporting the outcome of a calculation that I've performed. But what it means, I don't know. But let me just
In
say
fairness to Chandrasekhar, and a lot of the premises here are hard to motivate. So,
well, I rather like the paper for a number of reasons, but I'm just saying that I'm not sure that it provides us with the edge that we need to solve this problem. Yes.
I guess presumably if you had a sufficiently rich matter model that you could construct an observer with properties of this observer, then that matter model would also presumably give you a positive probability.
Well, it's confusing, right? Because if you wanted to see something like a world line with a lot of entropy come from, standard model, it would be a pretty far away from the saddle. It's a very non-perturbative thing to see, people at the time of reading.
Yeah.
Okay, so let me conclude with a discussion, since I think time is
the
over.
Factors of I go away in the Chandrasekhar calculation.
Oh, yes. Yes, there are no factors of I. But it's a different calculation.
Because of one world line.
Well, again, this is not the sphere, remember.
It's a different calculation.
It's a different calculation.
Yeah.
It's not the sphere coupled to an observer. It's the norm of the Hartle-Hawking coupled to an observer.
Right.
So the it's a different calculation, and there are no factors of I.
But before your calculation ended up being 0, there were factors of I to the d plus 2 as well.
No.
There weren't.
No, that's just in the sphere.
That was in Boltzmann.
No, the actual number which multiplies the 1 over infinity is positive.
Okay.
Yes.
Well, is there anywhere in your calculation that is sensitive to this cap-off point? Because all of your calculations seem to be done at near the bound.
It is sensitive to the capping off point in the integral in an indirect way, but this is much more obvious if you do the calculation at finite time.
Wow.
An example of finite time is t equals 0, which is right at the cap.
Okay.
What's confusing there is that you might have thought that if you glued a cap to another cap, you'd get the sphere, but you have to be careful about what you mean by the inner product in Lorentzian geometry. Anyway. So we've studied the quantum mechanics of the Hartle-Hawking state, the Hilbert space in which it lives to a certain degree, and its norm, by which I mean the Hilbert space in which it lives. I mean, we're integrating over these gammas mod diff times y. We found that the norm is 0 to 1 loop, and even with field theoretic matter, and I said it may persist in higher loops, but in fact, as of last week, it does actually persist to higher loops. And this further brings into question the phenomenological relevance of the Hartle-Hawking state and what might replace it. That's the key punchline. Let me make 2 comments on this, and then I'll conclude. So there's some ongoing work to try to understand how this interfaces with the inflaton, which again has this other issue that the inflaton wave function is not normalizable. So at least in the slow roll approximation, if you went into other regimes, then that's the structure of the wave function changes. So we'd like to understand what's going on in the context of inflation. But I just want to point out that the Hartle-Hawking wave function already has this one issue that it predicts that the universe, the spatial curvature should be very, very large, which it's not. It would be great if there was some way of ruling out the Hartle-Hawking wave function, maybe because in a more realistic situation, you would want to show that it has 0 norm. Once you couple it to the actual matter fields that you want and understand what's going on with the inflaton. And maybe that forces us to look at the higher topologies, for example. That's a speculation.
Didn't you say that it produces the correct on-loop predictions from the CMB or something?
Well, it does the right Gaussian fluctuations, but it also really incorrectly predicts the spatial curvature. So if you ignore that horrible, incorrect prediction, then the other ones look good. So
these other topologies will also give us the correct Gaussian fluctuations.
Depending on what you're looking at and what you mean exactly by higher topologies, also if you're willing to look at Coulomb-Deluccian subtons and stuff, that there are other types of contributions which don't have this problem.
So what do you conclude? Do you conclude that Hawking-Hartle is taking us down a wrong track?
I think that the idea of the no boundary state is the right track, but I think that the leading contribution is the wrong track. And I think that we can try to make precise how to deal with the subleading corrections to Hartle-Hawking and try to understand their phenomenological relevance, but that the calculations that people have been doing since the 80s with the norm of the Hartle-Hawking state need to be seriously revisited in light of understanding carefully the one-loop corrections.
But why do you think it's on the right track if it's giving us all these problems? It doesn't fit.
The leading contribution is giving us these problems, but there's other contributions that have been less studied that look more promising.
Do you think 2 loops is going to save us?
No, it doesn't.
Okay.
It's not the loops that save us, it's the topologies.
I see.
I'll say what the speculation is for 1 second, although this is a little bit aside. If you're interested separately in the question of what is the relationship between the norm of the Hartle-Hawking state and the sphere partition function for academic reasons, but we are, in fact, academics, is that I said that the norm of the Hartle-Hawking state is 0, but something that you could try to do is that if you tried to, instead of gluing a bra to a cat, you tried to glue a cat to a cat, or a bra to a bra. K is like some complex conjugation. You might wonder if there's a way that you actually get the sphere and you could also get the complex conjugate of the Hartle-Hawking of the sphere partition function answer. There's a bit of an ambiguity. So there might actually be a way of making this precise.
K is related to time reversal.
Yeah.
Is there some other motive? Yeah.
Well, it's to say that you wouldn't expect that this inner product, first of all, would be real. Just a comment. And there's some preliminary indication that you might, in fact, get the right factors of I. So there might be a way in which the sphere calculation that Polchinski did sort of relates in a sort of roundabout way to the norm of the Hartle-Hawking state. Not literally the norm, but more like trying to integrate the bra against the bra or the cat against the cat. That's the only speculation. That I think, it's not obvious what, if anything, that has to do with the cosmological implications, but if you were curious about the connection between these calculations, then here's an insight for you.
Great. I think we should probably stop there since did you have any last word that you wanted to?
No, I'm happy to answer further questions.
Okay, so let's thank Jordan. We have the colloquia starting in about 25 minutes at the basement.